Hello, welcome to lecture number 15 of CS204 Computer Architecture. So today we will discuss the data path design when the pipeline facility is available to the processor. So previously we discussed the data path where there was no pipelining concept involved, but today we will extend that data path and include pipelining. Please note that after this point, most of the content of this lecture is pre-recorded. So pipelining facility means there are multiple stages, right? And each stage is taking one cycle. Fetch is taking one cycle, decode is taking one cycle, each stage is taking one cycle each. So in that case, how we will design the control signal, how we will design the data path, that we will discuss in this section. So before starting this section, this is section 4.6. You have to understand these points. I think I have explained it many times. You already know what happens in fetch stage, what happens in decode stage, and execution stage, memory access, write back. You already know all these things, so I am not explaining it here. I'll directly go to this. I hope this data path is clear to you. This diagram is known to you. All the signals are known to you. So now you can see there are some, this section is fetch, this is decode, this is execute, this is memory access, this is write back. And you can see there are some dotted lines here to separate the module. Now to understand this concept, you have to understand the one important logic here, that suppose there are two instruction 1 and instruction 2, inst1, inst2. There are two instructions. First instruction will start fetching from this cycle. Suppose this is cycle 1, okay, this is cycle 2. Second instruction will start fetching from this cycle. So now concentrate on this module. So we don't have separate data path for each instruction. Like the way, if you cannot say that instruction 1 is using one fetch module and instruction 2 is using another fetching module. That's not the concept of pipelining. That is called multi-core architecture, right? That's a different thing. Here we have the same hardware module, and the same hardware module, cycle 1, in cycle 1 that module is using by instruction 1 to fetch an instruction, and then cycle 2 the same module is using by instruction 2 to fetch the instruction. So the problem, the logic here is, at first cycle this module will fetch instruction 1, and at the end of first cycle this module must store instruction 1 somewhere here. Why? Because in the next cycle, cycle 2, this module will use to fetch a new instruction, that is instruction 2. But what the first instruction will be doing in cycle 2? Then cycle 2 will perform the decode of this first instruction, right? Will perform the decode. Who will perform the decode? This module. This module is performing decode. So this module need, at cycle 2, concentrate here, at cycle 2 this module need which instruction? At cycle 2 this module need instruction 1, right? So that's why we have stored the instruction here. So this module will take instruction from here and start executing. That point is very important. So in pipeline phase, in every stage, in every module, suppose at cycle 1, or let me write it cycle x. At cycle x, any module, if it's performing some operation, that at the end of this cycle, this result will be written in a temporary location here. This is called pipeline register. The result will be written in a pipeline register, such that in the next cycle, when this module will start working on a new instruction, the old data that is stored here will be used by the next instruction, next module here. For otherwise you cannot communicate between these stages. So if you go here, the same thing they have written here, so you can skip all this thing, or you can just quickly read it once. If you go here, you can see there are 4 register. These are called pipeline register. This is called fetch decode register. Why? Because it is in between the fetch and decode stage. This is called decode execute register, execute memory access register, and memory access write back registers. So how this works? So let us go for a load instruction. If we go for a load instruction here, how it will work. So I'm quickly explaining the first basic here. In every cycle, if it is performed some working, then after at the end of the cycle, it will write all the temporary result in this register. Okay. And at the beginning of every cycle, this module, what will take at the beginning of every cycle, this module will read data from this register and start performing operation here, and at the end of that cycle, it will write the temporary result in this register. In this way, the data is flowing from one stage to another stage. And you may ask that in at a particular cycle, from this register, this one is writing and this one is reading at a particular cycle. So is there any conflict? No, the conflict will be resolved by that concept, like in one half we are writing and in another half we are reading. So with this, there will be the conflict will be resolved. Okay, so you have understood all these things. Now let me explain one example. Let me go with load example. Suppose load x5 4x6. How we can perform fetch stage. If I go for fetch stage, if I go to fetch stage, let me write it here. Fetch for load. So what we will do, we'll perform the fetch here. We'll perform the fetch here, and at the end of this, instruction will be stored here. See, the instruction is storing here in this register, and with this we need to also store the program counter here. Program counter is important. Why? Because in next cycle, suppose if this is if this is cycle 1, if this is cycle 1, in next cycle, suppose there is a instruction here called instruction 2. So in next cycle, in cycle 2, this will start fetching new instructions. So it means that at cycle 2 the program counter value will change. So in sometime we need the old program counter value for PC addressing and all, right? So we need to store the program counter value also. At the first cycle here, we will fetch the load instruction. After fetching, at the end of cycle 1, we will store the instruction here, we will store the program counter here of operation of cycle 1 done. I am only explaining it in terms of the load instruction. What will happen in cycle 2? In cycle 2, we will perform the decode here, right? We will concentrate on this here, we will perform the decode. So what will happen in decode? In decode phase, what we'll do, we'll try to decode the instruction, and based on this instruction mapping, we read the registers. So in that case, what register we need to read? We need to read x6, and 4 will be passed as 12-bit constant, right? So the instruction that is stored in this register at the beginning of cycle 2, what decoder will do, it will read the temporary result that is stored in this fetch decode register, and what it will read, it will read the instruction, that is 32-bit instruction, and based on this instruction, it will send x6 here as x6 as rs1. Okay, and then the 32-bit instruction will be sent through this, so the 4 will be written here. So what we are doing, so at the end of decode phase, the value of x6 will be stored in this register. This 4 bits, you can see there is a line going from here to here. So the 4 will be converted to 64-bit value, and it will be stored it here. Okay, and the program counter value is also transferring here. So what is the difference between this data path and the data path that we know from single cycle? There is not much difference. Only thing is we are passing value from one pipeline register to another pipeline register. We are not directly giving it to another module. If you remember the previous data path, from that, in that data path, we are directly connecting register array to arithmetic logic unit, right? But here we are not doing, because it is not a single cycle operation. Here every result, every outcome of every module, we are storing it in a register called pipeline register. Okay, and that's why we are also forwarding immediate value here. Now you may ask a question, sir, why you are transferring immediate value from this register to this register? Because if at cycle 2 we are performing the decode here, right? At cycle 3, what will happen? At cycle 3, this decode phase will be used to decode the second instruction. So it means that at cycle 3, whatever information I am storing here will be overwritten, right? Will be overwritten, because at the end of cycle 2 only, because here Maybe I'm confusing. I'll start from this point again. At cycle 2, what is happening? At cycle 2, decode phase is reading from this. At the beginning of cycle 2, decode phase is reading from this register and it will start its operation. But at the end of in cycle 3, fetch will also happen, and fetch will fetch the second instruction. So at the end of cycle 2, fetch will also write something in this. So it means that at the end of cycle 2, the content of this register will be overwritten, right? So at cycle 3, if I want to decode if I want to execute it here, so for this execution here, in this execution, we need this 4, we need 4, right? But that 4, if I don't pass from this register to this register, then it is overwritten. So that's why whatever result we need in a particular module, that result must be forwarded. That's why the value of x6 will be forwarded here, PC will be need to be forwarded here, and this immediate value also need to be forwarded. You cannot just keep store it here. If you store it here, it will be overwritten, so that when you will perform execution here, you cannot get it. The same thing here, you can see now x6, if I only go with load instruction, then x6 will be required here. So in execution phase, that is in cycle 3, x6 will be supplied from this register, okay, and 4 will be also supplied from this register. Now it is stored here, 4 will be also supplied through this line, okay. So effective address will be calculated and effective address will be stored in this register again. And with this see there is a line here. This line is not required for, I think, load, so I'll later explain it. Now at 4 stage, I'll go for memory access, right? At cycle 4, I'll go for memory access. So at the beginning of cycle 4, this module will read the effective address from this register and to start accessing the data. It will access the data and it will load it, it will store it. At the end of cycle 4, it will store the result in this register, okay. And at cycle 5, when I'll perform write back, see at cycle 5, when I'll perform write back, now it will read the data from this register and it will write it back to the register file. This is how a pipelining works, and there are intermediate register, how this register are works, that also I have explained. But there is a small issue I have said. See, when you are performing write back, we are performing write back at this stage, at stage 5, and where we need to perform the write back, if you see the instruction, we need to perform write back in x5. See here, we need to perform write back in x5. But at this stage, how you know that you want to write it in x5? Because you have not forwarded anything regarding x5 here. See, you have just forwarded 32-bit instruction, you have forwarded x6, you have forwarded PC counter, that is fine, but you have not forwarded x5. So at this stage, how you will know that where you will write? So there is a mistake in this data path. In this data path, along with this 32-bit instruction, you also need to forward this rs1, or you can say rd. This is rd, right? This x5 as rd you have to forward. The rd you also need to forward like this. Then only at this stage you can say, okay, I want to write it in x5. Otherwise your x5 will be lost, it will be overwritten by some other instructions. I hope it is clear. In this chapter, what they did, they have designed multiple diagrams to explain load, add and store for in this similar fashion. I hope you'll understand it. Now I'll quickly explain some more arrows here. So what do you think, why this arrow is required? This arrow, what it is doing, it is basically forwarding rs2 here. It is basically forwarding rs2 to this stage. Why it is required? This is required for store, right? If there is a store instruction x5 for x6, suppose, concentrate on this this store instruction. So in this case, this x5 is your rs2. Suppose if this is your rs2, then this rs2 is required. In which stage it is required? It is required in memory stage, right? Memory access stage. In memory access stage only will write this rs2 into memory. So in this is the memory access stage. So in this memory access stage, you must pass rs2. That's why this rs2 is passing and it is storing in this temporary register, so that if the instruction is a store instruction, then it can use it. I hope it is clear. And you can also see one more interesting thing here. There is a uh, arrow like this. Why this arrow is required? This arrow is required for add instruction, because if it is a load instruction, you are getting data from here and you are storing it here and you are writing data back here. That is fine. But if it is a add instruction, then your result will be ready after this ALU section, right? So you have to bypass your result from here to here, so that at the write back stage, if it is the add instruction, then you can also write the result from here to here. So all this thing is important. So if we scroll down this chapter, they have explained this use of pipeline register for load and different type of instructions. The explanation is same as it is that I have just shown you. Only thing is you have to understand is the diagram. As I have explained you that if the color is in the right side, then you have to understand there is a read operation. If the color is in the left side, you have to understand it's a write operation. So what the load instruction is doing in the first cycle, it is read from instruction memory, it is reading from instruction memory, and then at the end of this cycle, it is writing all this thing in this register, writing the instruction and program counter here. That's why here the color is in the left side. Now in the next cycle, what we will do first, at the beginning of this cycle, in second cycle, decoder will read data from this register. That's why color is in the right side, and then it will perform the decoding and all, and the end of this cycle it will write that result back in this register. So to understand that's why the color is once in the right side and once in the left side. So with multiple diagrams here, they have explained this concept that I have shown you, that and the same concept that they basically they have explained why these pipeline registers are important, and how we have to forward data from one stage to another in pipeline. uh, uh, okay, so I'm not explaining all this thing. You read it from book, you'll understand it. If you have understood my load and store example and forwarding that I've shown here at the beginning of this section, then remaining thing you will easily understand. I no need to explain all these things. They have just used multiple diagrams one after another to explain these concepts. And I think all this thing I have already explained. Graphical representation of pipelining. Yeah, this section is not actually directly connected with previous section. This is, but yes, this section is important, because if you start reading this section without and if I don't explain it, maybe you'll become confused that what they are trying to say. So what my advice will be, you can ignore this section. They said how you can graphically represent pipelining. So graphically representing means, as a reader, if you write in exam, if you write a book, if you write a paper, how you can explain pipelining. So what I will advise you, every time you write pipelining like this: fetch, decode, execute, memory, write back, right? Then if second one will start from here: fetch, decode, execute. You write every time like this. If forwarding is required, you write forwarding like this. You use this, assume that all are taking one cycle like this. This will be the easiest way to represent a pipelining, and you can ignore this section. Okay, pipeline control, this is also a subsection here. Pipeline control means, now you see, if you see the data path in single cycle data path, there are no this kind of pipeline registers. Sometime in pipeline, if in pipeline register, we also need to forward some data from one pipeline register to another pipeline register. So in this situation, what will be the control signal? See, we need control signals here, right? We need a control signal here, we need a control signal here, we need a control signal here, we need control signal here, we need some control signal here also. So all these control signals required, I have explained in last lecture. So how to generate all these control signal. So if you don't remember the control signal, maybe first quickly watch again my lecture 8 and then start with this subsection pipelining control. Pipelining control is very simple. Why I'm saying very simple, because if you remember lecture 8, I have explained you that most of the control signal are generated in the decode phase, right? Because from the opcode only you will understand most of the control signals. I'm showing the figure here. You can see the top right corner. I'm showing the figure. You can see most of the control signal we have designed from the opcode. Okay, and some other control signals, that is LU output and all, that we can design with some additional information. Okay, only additional information that is coming out is the zero is also required for branch. So it means that if most of the control signal we can generate in from the opcode, then let us generate in the control in the decode phase. What the pipeline is doing, I think I'll not go for all this. These are the control signal required. Okay, uh, so what I'll do is, why I'm scrolling it, because it will help you when you'll read the book. See, I'll design all the control signal here from the opcode in decode phase, and then I'll store all the control signal in these registers, and I'll pass this control signal through this register from one register to another register like this. Because if there is a load instruction here, and then there is a stored instruction here, there is a add instruction here, then for this load instruction control signal will be different, and for this add instruction control signal will be different. So suppose at cycle 2, when I am when the computer has decoded load instruction, its control signal are different, right? So just generate their control signal and then store it in these registers, and then pass it through this register from one register to another pipeline register. Why? Because the add instruction, the next time this module will execute add instruction, means will perform decode for add instruction, and new control signal will be generated. So to preserve the old control signal, the control signal for load, you just simply pass them from one pipeline register to another pipeline register, and that's it. That is enough to understand the control signal of pipelining. Okay, so I'll not explain it more detail. Try to understand it by yourself. Read this section and try to understand. The only thing you have to assume here, that we have not explained how to generate control signal to handle hazards, that is data hazard, branch header. That I have not explained yet, but I am assuming that if there is no hazard in this pipelining, then you can generate control signal in this way and pass it. So try to understand this section. Now let us start a new section 4.7, which is data hazards, forwarding versus stalling. I think all the terms here, data hazard, forwarding, stalling, all these things are known to you. So why this section is important? This section is important because in this section we'll try to understand that how you can design a data path which will support data hazard, which will support forwarding, which will support stalling. So all these things I will try to understand in this section, because before this section we have designed first we have designed data path without considering pipelining. That was a single cycle data path. Then we have designed a data path including pipelining, but assuming that there is no hazard. Now in this section we will design data path assuming that there is pipelining plus data hazard, but again we will not assume there is any control hazard. In next section we will discuss about pipelining with control hazard also. Okay, so what I'll do today, I'll not go for any whiteboard explanation today. I'll only explain from this book. Why? Because most of the thing is known to you here. Whatever thing I'm going to explain from this section is very easy, will be very easy if you know all the previous concepts. So again, as I remind you in every lecture, here also I am reminding you that if you have not watched my previous lecture, then please go and watch those previous lecture first. Try to understand them and then come here. Otherwise it will be very difficult for you to understand. Though the concepts are easy, but it will be difficult for you to understand. Okay, So we'll start with this example here. You can see there is an example here. This is a example. Concentrate on these instructions one by one. First instruction is sub instruction, and concentrate on the bold register. This is the x2, and after this you can see there are four more instruction: and, or, add, and sd. All these remaining four instructions are using this x2, which is updating by the first instruction sub. So it means that all the remaining four instructions are data dependent on the first instruction, right? Because all these remaining four instructions are using x2, which will be written by the first instruction. If this point is not clear, then you can pause this video here and try to understand why I am saying this. Okay, so I'm going forward assuming that you have understood it, that all the remaining four instructions are data dependent on the first instruction. Fine. Now the next question is, can you solve it using data forwarding? Let us write the code here, right? For the first instruction, fetch, decode, execute, memory, write back. Second instruction will be from here, right? Fetch, decode, execute, memory, write back. Can you solve this problem using forwarding? What about the first instruction? First instruction is sub. I'll only write the first instruction here, sub. So when the result will be ready? Result will be ready after the X instruction. Assume that there is a register here in between, right? You know this is called pipeline register. I'll not draw it everywhere, but I'm just drawing it here for you. So you have to forward the value from here to here. Why? Because after this execution stage, you know the concept of pipelining register now after the previous class. So after the execution state, I'm saying about the first instruction, concentrate on first instruction. So in case of first instruction, after the execution stage, the final result is already ready, right? Final result is ready and it will be on this register. After the execution stage, this pipeline register, final result is ready. Now in case of second instruction, if I concentrate on second instruction, the second instruction, execution will start here in this place. So in when execution will start, it should need the updated value of x2, which can be forwarded from the above register. Okay, above pipeline register. Now let us go for the third instruction. Third instruction will start fetching from here. Fetch, decode, execute, write back, memory, write back. This instruction, there is a third instruction I'm saying about this or instruction here. You can concentrate here on this instruction or instruction. So this instruction also need x2, right? So do you think it can read from register? I don't think it can read from register, because this x2, if it can read from register, then in which stage it will read? Reading from register is done in decode stage. But see, in decode stage here, the first instruction will not write the result in register. When the first instruction will write the result back in register, the first instruction, there is a sub instruction, will write the result in x2 register in after this stage. This is the write back stage. And here if you concentrate on this third instruction here, third instruction will decode in this stage, which is before the write back of first instruction. So again, when in during the decode phase, the third instruction will read a old value of x2, right? No problem. But in execution phase, we must supply the updated x2 value. So how, from where we can forward? So we need to forward it from this register. It will be forwarded from this register. How? It means that after execution, here concentrate on the first instruction. After execution, result will be stored here. Okay. Then next phase, what we will do normally from pipeline register, we will read all the values from here, perform execution here, and write the data back here. So this is the property of pipeline register that I have explained in last class. So what will happen here? What will happen here, that after execution, when we'll go to the next phase for instruction 1, I'm saying about only instruction 1, we'll read data from this register and will perform operation here if it is if any operation required in this stage, and then we'll write all the results here back in the this register. And what will happen including this, the result that is coming from the execution stage will be copied from this register to this register, and this copying is required. I think this path I have already explained in previous class, that this data path is required. This there will be a connection from here to here to copying the data from here to here. If it is not clear, you can go and see the data path of that I have explained in last class. So now your result value is here, so from this register you can forward it to here, to this ex. So in this way forwarding is also possible. So you can see there are two possibility of forwarding. First time it is forwarding from the pipeline register, that is just after the execution stage of fast instruction here, and then in second case the data is forwarding from the pipeline register which is after the memory stage, right? So there are two different register pipeline register from where the data can be forwarded. If we go to the fourth instruction, you can say this is the fourth instruction, add instruction. So for this fetch will start from here, decode will be here, right, and execution will be here, memory, write back. Do you think forwarding is required here in this stage? You can pause the video here and try to understand what I'm saying. Try to answer this question, that do you think forwarding is required for this fourth instruction, that is the add, this one, fourth instruction. Okay, I hope you have you already guessed the answer. In this case forwarding is not required, and the decode will read the correct values or updated values. Why? Because in this cycle only write back will be performed for instruction 1, and if you remember I said that write, we normally consider that write will perform in the first half of this cycle and read will perform in the second half of this cycle. So even both this here write and decoder performing are in same cycle, but write will be performed in first cycle and decode will start from the next cycle. So there will be no forwarding required. Decode will read the updated value from the register. So if there is no forwarding required in fourth instruction, then obviously the fifth instruction also, for fifth instruction we don't need any forwarding. You fetch, decode, execute, we don't need any forwarding. So I hope this is clear. And for the same example they have explained lot of things here, and ultimately they have given a diagram like this diagram only shows the dependencies. I have already explained it in my example, but if you see their example they are showing it here, then you can consider this as fetch, decode, execute, memory, write back. So they are saying that if this, for this sub instruction, the value x2 will be written in this stage. This is the register stage, right? Write back stage means this stage only it will be written in the register. And see the colored is in first half, means it is a write operation. So, and if you concentrate on the next two instruction, these two first instruction need to read the register in this stage. This is the decode stage, right? This is the decode stage for instruction 2, and this is the decode stage for instruction 3. So these two register, these two instruction want to read x2 register before it is written back. So that's why there is backward lines here. See, this is a backward line. These two are backward line. So backward line means forward, means it is not possible. We have to do something to handle it, otherwise we need to go for stall. Here this is not backward line, this is the correct line. This is the forward line, so no problem. So to handle this we can use forwarding, that I have already explained. So I am not going in detail with this diagram, you can read it here from here. And then I think they have explained forwarding and all. I'm excluding this, all these examples here also. You can read all this concept once you'll understand it. Now what I will explain you is This is the forwarding they have explained. So I'll explain the same forwarding, but in my way first. Okay. uh, Let us again write. This is fetch, this is decode, this is execute, and this is memory, this is write back for first instruction. For second instruction, this is fetch, this is decode, this is execute, and this is memory, this is write back. Right. So how they are forwarding? Forwarding is happening, but from which location to which location? It is happening from this register to this. So these are called pipeline register. This register is called fetch decode register, because this register is placed between fetch and decode. This is called decode execute register. This is called execute mem register, and this is called mem write w register. I hope you are getting this pipeline registers and getting the concept of pipeline register, and the name is also very easy. IFID register means the register pipeline register between fetch and decode. Okay, so now after this execution stage of instruction 1, the result will be stored in this register, this xmem register, right? Xm register. Okay, this is available here. This is which cycle? Cycle 1, cycle 2, cycle 3, cycle 4, suppose cycle 5, like this it is going. So after cycle 3, the result is available here. So at the beginning of cycle 4, you can see here at cycle 4, the second instruction will execute, right? And when second instruction will start execute, we need the value of x2, which will be forwarded from here to here. Very easy. So now here, when this forwarding is happen, if you see this example here, I am writing like this because both are R type instruction. Consider like RD, RS1 and RS2. Okay, so when this forwarding is happening, here let me write here also RD, RS1, RS2. So if the RS1 or RS2 of second instruction is depend on the RD of the first instruction, then only the forwarding is required, right? This forwarding is required. So let us write all this condition here, because I hope you understand what is called forwarding. So now my intention is what to do to perform this forwarding. Forwarding is very easy if we just try to write a diagram here, or if I give you just give you a question like this in exam, that check, given the instruction set, check if forwarding is required or not. Very easy. But that's not our job here. As we are discussing computer architecture subject in a PG level course, at least you should know that how to design, or what are the controller, what are the hardware unit that we need to design such that this type of forwarding can be performed. So I'll explain this with from here. This is a simplified data path design, where you can see the ALU signals are showing here, and the pipeline diagram registers are there. It's a simplified version. Okay, all the necessary things are there. You can see there should be a multiplexer here which will decide between the RS2 and let me write here, this is always RS1, right? And this is always RS2. So here this lines, there should be a multiplexer here to decide between RS2 and the immediate value. But assume that there is a multiplexer here, but will never show it here. So because we have hidden some other concepts so that we can explain the concept of forwarding here. But don't think that these those concepts that we know are previously are not required. We have just removed them and make the diagram simple here to understand the concept of forwarding. Okay, to understand this, let me write two program here, two instruction here, x2, x4, x5, and then sub, x3, x2, x4, x6. Okay, is there any dependency? Yes, there is a dependency, right? The second instruction is using x2, which will be written by add x2. And always remember the format. The R type instruction will be written like RD, RS1, RS2. Okay, and every time when we read a instruction, if we go here, then rs1 will be available through this line, rs2 will be available through this line for r type instructions. Okay, so now from where you need the forwarding, if you write the pipelining here for this, sorry, so if I write the pipelining, so for first instruction, fetch, decode, execute, memory, write back. Second instruction, fetch, decode, execute, memory, write back. So forwarding will be performed from which to which? The register that will be here. I'm saying our pipelining register, from here it will be forwarded to this. Okay, but the concept here is, if we go back to their diagram again here, see, if you go back here and if you see the forwarding happens, it looks like that each instruction has the independent data path. Like they are saying that they have designed the arithmetic logic unit here also, and saying you this arithmetic from this register it will be forwarded to this arithmetic logic unit. It is the way the diagram is drawn, it looks like that each instruction has separate arithmetic logic unit, but that is not true, right? In pipelining, the same arithmetic logic unit are using, so these arithmetic logic unit and this arithmetic logic are the same component, but they are using in two different cycle. That's why we have designed it two times. So this line means what? If I go to this diagram again, means this is the memory. So there must be a line, from here to here, right? There must be a line from here to here. Why? Because concentrate on the first instruction only, concentrate on the add instruction. So for add instruction, after the execution phase, the result will be ready, right? Result will be ready here. So assume this is the result is ready here. So where the result will be written? Result will be written in this register. So from this register, in case of forwarding, forwarding means in the next cycle, when this execution unit, the same execution unit, when this execution unit will be used for the second instruction, then we need to forward data from here to here. Means we need to forward data from this register to here. Okay, this register to here. So there should be a connection from here to here, like this. Now let me change this little to a let me write here that this is x6, okay, and this is x2. Now your x2 is rs2, right? In case if you concentrate on the second instruction, that is sub instruction, here your x2 is rs2. So then also your forwarding will be fine, right? We need to forward the result from this x to this x, but not in this age, right? We need to forward data to through this age. Now this rs2 need the updated value. Okay, so in this case the value need to be sent from here to here, right? Are you understanding what I'm saying? So it means that the result that I have stored here, okay, for the first instruction, that is the add instruction, these result sometime need to be forwarded here, or sometime need to be forwarded here, okay, or sometime it is not required. When it is not required, suppose it is not x2, it is x4. Do you think there is any dependency now? Here there is no dependency. If there is no dependency, it means that which result should be taken by the arithmetic logic unit when it is executing the second instruction, it should go with this rs1, it should go with this rs2. No need to use these forwarded lines, right? I hope you understood this example. Now let us write one more instruction here. After this, suppose there is one more sub here which is using suppose it is x10, x2, x14. Okay, now Concentrate on the first and third instruction. So first and third instruction, do you think there is any dependency? Yes, there is a dependency between x2 here, right? Add is the first instruction is writing something on x2, and the third instruction is trying to read from x2. So if I write this here in this left top left corner, then for third instruction fetch will be here, then decode, then execute, then memory, then write back. I have already explained you that forwarding will be performed from this register to here, right? What is this register? This circle means which pipeline register? This register, MW, right? Memory W, because this register is between these two. So I think this point I have already explained, but I am repeating it here. So concentrate on the first instruction. If you concentrate on the first instruction, the result is ready after the execution stage, right? Here result is ready after the execution stage. Now in the next cycle, the first instruction will be in this stage, memory stage, right? In memory stage, though this is a R type instruction, there is nothing to do in memory, but there will be no operation in memory stage for R type instruction. But you can see there is a connection here. What is the purpose of this connection? That result is forwarded in the next cycle when this memory cycle will be executed. Means this cycle for instruction 1, the result from here will be from this register, this vertical this pipeline register, it will be copied from here to here. Okay, now result is here. So now if the third instruction here in this execution phase wants the value of for that result generated by instruction 1, not instruction 2, generated by instruction 1, then that result is not available in this register. Now this register is already updated by the second instruction, so the result is available in this register, the last pipeline register. So what to do? There's it is rs1, right? X2 is rs1, so there should be a line from here like this. Okay, that should be a line like this. And if this is x4 and this is x2, then there should be a line like this. Are you getting my point? There should be a line like this. So now I think it's a little bit complicated now, but if you are following me from the beginning, then I think it's a simple idea that why there are two additional lines coming in this first input of ALU, and why there are two additional lines coming in the second input of ALU, because there are two possibility of forwarding here for both the inputs, right? First possibility is forwarding from xmem pipeline register, and second possibility is from memory write back pipeline register. So all these forwarding possibilities are there. So now obviously these three input cannot go here, right? So there should be a multiplexer here, right? That should be a multiplexer here which should decide that among these three input which one should go. So then it means that there is a multiplexer required here also, and with that there we need a control line also here, right? The control line will decide that which among these three should go. Okay, now let me write a simple example again so that the things will be clear to you. Let me write the same instruction again here: add x2, x5, x6. Okay, and then I'll write sub x4, x3, x7. Okay, for this now what should which value should pass through this line? If assuming the execution of second instruction, which value should pass through rs1 among these three? I think this one, right? The original connection, there is the original register value should pass. Forwarding values are not required. About RS2, the same thing. Forwarding values are not required. The original value should pass through this multiplexer, right? So the signal value will be accordingly. Select line should be accordingly. Now if I write here x2 instead of x3, this is x2 because this is x2. So if this is x2, now that is a dependency. So now for in case of rs1, which value should pass? The value should pass is this one. This value should pass. Out of these three, this value should pass through the multiplexer. So the select line should be accordingly set. Okay. And if suppose this is 4 but this is 2, then which line should be select? Then in case of rs1, the original line will go, this register will go. But for rs2, this line, the line coming from this register, this line should select. So this select signal will be accordingly set. So I hope it is clear. So now let us go to this diagram. In this, within the same page, this second diagram is there. So there are two select, see the there are two multiplexers they have designed, and they have written the lines here. The lines are same as I have drawn the lines, but so let me number this line 0 1 2. Okay, 0 1 2. So you can see 0 is the original register line. Okay, and see there is a forward A here for this, and forward B is here. That these are the control signal, two control signal. Who is generating the control signal? By forwarding unit. Okay, so now in this case, if I go for the previous example again, then what will be the value of forward A and forward B? Again I am writing it here, add, okay, x2 x6 x5, okay, then add x7 x2 x3. In this case, what should be the value of forward A and forward B? Tell me. The value of forward A, is there any dependency? Yes, there is a dependency. So forward A should be which one? Forward A should be 1. Sorry, for this we have to understand what is 1, from where 1 is coming. So 1 is coming from memory, okay, and 2 is coming from execution. So here the value should be 2. Value should be 2 because the value that is coming from here, see, the value that is coming from here is 2. Okay, so this should be go. Now if, and here in case of this example, the example that I have written here, what should the value of forward be? Forward B should be 0, right? Forward B should be 0. The original value should pass through this multiplexer. Now let me change this. Now suppose this is 3, okay, and this is 2. Now what should be the value of forward A and forward B? Forward A is 0. It should pass the original value in case of RS1, right? But what should be the value of forward B? Forward B should pass the value of the forwarding value. So here the value should be 2. I hope you are getting it, right? Now let me add one more instruction here, sub x7 x2 x4. Okay, x4. Now concentrate on the first instruction and the third instruction. Do you think there is a dependency? Yes, there is a dependency, right? So and this can be resolved by forwarding, but you know from which it will be forward. In this case, in the during the execution of the third instruction, you need to forward the result from the last register. So in this case, what should be the value of these two value? What should be the value of forward A? Here the value of forward A should be 1 and forward B should be 0. Why 0? Because in case of forward RS2, again the original value should be there, should go, right? If I now change this instruction to x4 and x2, now what will be the value? The forward A will be 0 and forward B will be 1. So in that case, the value from this register, pipeline register should go here. So all these things are decided by whom? So here I am saying that if this is the case, then forward 1 should go. If this is the case, then forward A should be 1. If that is the case, then forward B should be 1. So or 2. So means if else whatever I'm saying, it's a logic, right? It's a logic. Based on this logic, this 1 0 1 0 are deciding. So if you go down in this, see, this is the logic. This is the logic explained in this table. So this logic must be implemented in a circuit, and that circuit should control this line, and this circuit is called here forwarding unit. So like a control unit that we have understood previously, here there will be a forwarding unit, and this forwarding unit will decide all these things. Now the question will be how to design the forwarding unit and what are the information required by this forwarding unit to take these decisions. So these now we'll discuss. So for this, again we'll start with a small example. So again, let us consider this simple idea. Again, it's a very simple idea, but and assume this this format RD, RS1, RS2. I think it is already remembered to you, but I am repeating it multiple times because it is important for this case. Now you know forwarding is required, you know what should be the value of A, but how you are deciding it? You are deciding is because there is a logic, and logic I'll write here. Logic is if there is when forwarding is required here, if the RS1 here or RS2 means any of this, if either this is X2 or this is X2, forwarding is required, right? So if RS1 or RS2 of second instruction here is depend on the RD of the first instruction. So now assume that when this forwarding unit is where, if forwarding unit is in execution stage, right? So second instruction, so the information of second instruction, the forwarding unit, check the forwarding unit is here, right? So what this forwarding unit is required, forwarding unit is required this instruction, this information of this instruction is stored here in this register. This register is currently supposed storing the information of first instruction, and this register is storing the information of second instruction, right? So what we need to check here is that if xmem, I'm writing em, xmem rd, okay, means in this register, the destination register that is stored, if this is equal to IDEX, okay, I'm writing IDEX RS1, or if xmem rd equal to IDEX dot rs2, then forwarding is required. Are you getting my point what I'm saying? Because this add instruction when assume the execution stage of second instruction. I have written this if this fetch decode execution pipeline diagram every time, many times. So let me write it again here. So I have written it here, you can see in the bottom here I have written. So when the execution of the second instruction, this is happening, so it at that time during when the execution should about to start, means when this execution of second instruction is about to start, the info, so how it will start, I have explained it in last class that before starting any stage in pipelining, it will read the all the information from the left side pipeline register, and it will start its execution, and then after all this finishing, then at the last it will write all the information in the right side register. So when this execution will start, it will read all the information, means the second register, that is this register, second register is information of second register is stored in this IDEX register, and at that time the information of first instruction is stored in xmem register. So if you want to check whatever condition I'm saying, that if the RS1 or RS2 of second instruction is depend on RD of first instruction, then this type of forwarding should be there, means forward A should be 0, right? So we are checking the same thing here. Now see, EM means this is register particularly. If in this register the RD, this is the result stored, is equal to RS1 that is stored here, or it is equal to RS2 that is stored here in IDEX, then there should be a forwarding. Which forwarding? Forward A should be 0 in that case. Forward A means, in first case forward A should be 0, and in second case forward A means here, in this case forward A should be 1, and in second case forward A forward A should be 2, right? Forward A should be 2, and in this case forward A should forward B should be 2. It is very simple. Now if we go to this example, then you can if we concentrate on the third instruction, again there is a dependency between first instruction and third instruction, right? X2, but you know the forwarding in this case should be from the memory write back register, right? And here forward A should forward B should be 1, right? Forward B should be 1. So how we can check this? Basically here either RS1 or RS2 in this stage should if they are equal to the RD of first instruction here, then there should be a forwarding, and that forwarding should be from WB stage. So here we need to write, in this case again this start instruction is in IDEX at the before starting the execution, and the first instruction information is first instruction is now stored in this memory write back register. So the same thing we'll write here, only we'll write if memory write back dot RD is equal to IDEX dot RS1. In this case forward A should be 1, right? Or if memory write back dot RD equal to IDEX dot RS2, in that case forward B should be 1. So I hope you are understanding the logic here. The same for means so if you want to design a forwarding unit, what are the information you need? You need information of what are the RS1 RS2 of the instruction that is stored in IDEX stage. So see, RS1 and RS2 from IDEX are giving as input to forwarding unit. You need the RD from EXMEM stage as well as RD from MEMWB stage. So see, these inputs are also giving to this forwarding unit. So these 4 inputs are enough to decide this forward A or forward B logic which is given in this table. So based on this, I think forwarding unit it can be designed, and forwarding unit will give the appropriate values here. So if you want to understand it more detail, then read the book, you will understand it, because I am explaining it in a shorter way. More detailed explanation is given in this book. So if you are not understanding what I am saying, you can also read the book. And again, needless to mention that if it is still not clear, you can always ask your doubt to me. Don't think that you can only ask doubt on Monday doubt clearing session. You can also ask your doubt any day by sending an email or putting a comment on Google Classroom. Okay, so whatever I have explained, the same logic they have also written here, but I am not explaining it here. So maybe the syntax is little bit different here, but if you read the book, if you follow their book from the beginning, you will understand the syntax. Only the syntax is different, but the concept that I have explained, the same logic they have also written here, you will understand it now from the book. So now there will be a situation like this. This is a tricky situation here. You can see this instruction. If you go for this third instruction, then x1 is depend, you can see it is depend on both in first and second instruction. So from it means that from where you need to forward it from XMEM stage or MEMW stage, right? There are 2 stages: execution memory pipeline register or memory write back pipeline register. So in this case you can forward it from both the place, but which one is appropriate is the latest one. So it should forward here from execute memory stage. And so it means that if this type of situation is there, to handle this you need to change the control logic little bit, and it is written here, so I will not explain it here. Try to understand it by yourself. If this type of situation is happening, how to write the control signal. So I hope data path is now clear. I think if we ignore the forwarding unit, the remaining things I've already explained in last class. So the control signal is decided in decoder stage, and then all the required control information are generated and stored in this register. See, there are three sections here. W means B means all the control that will be required in WB stage, all the control that will be required in memory access stage, and all the control required in execution stage. Everything, all the controls will be stored here, and when the next execution will start, the execution controls will be used here, but next two these two controls should be forwarded here like this. So all these things I have explained in my last lecture. Here I am not trying to explain it. So what I am trying to say here is, if we exclude the forwarding unit here, the remaining things are already covered in last class. And here, this forwarding unit, the concept of this forwarding unit, I have just explained you, right? And there are some control signals required in forwarding unit. These control signals are coming from here. You can see this write back unit. Why this write back unit is required? Write back unit is required because if you see their logic, they have used write back result. Write back result is important because you need to assure that the instruction is the forwarding is a R type instruction, because if this is write back is on it, that it means that it's an R type instruction. Okay. Read the book, you will understand it. I have mostly explained it, only I have not explained these two control logic. This is explained in book. Try to understand it by yourself. So now I'm ignoring all this. This is, I think you will understand it by yourself. So I'm ignoring all this thing. Now next thing is data hazard and stall. Means till now whatever I have explained, it looks like that if there is a forwarding logic control unit is there, then everything can be resolved by forwarding. But that is not the case, right? I have explained it in last class that if there is a load instruction first and then a add instruction, then you cannot resolve it using forward. Like if suppose there is a load instruction, load x2 4 x3, right, and there is a add instruction here, add x4 x2 x10. So in this case, it is second instruction is depend on first instruction, and this this data hazard you cannot resolve using forwarding. You must need one stall, and that I have already explained in last class. So now here, if you concentrate on this example, load x2 4 x3, then add x3 x2 x10, and then there is a third instruction also I have written. So now when I'm executing the second instruction, suppose fetch decode. Now I need, suppose I have to perform the execution here, but for execution we need x2 should be ready, right? But here x2 it will not be ready, because x2 will be only ready after the memory stage here, because it's a load instruction. First instruction is a load instruction, so there should be a stall here. Okay, so if we are going for a stall here, then it means that in this cycle, so okay, there will be a stall here, no problem. So now going for third instruction, suppose, so if there is a stall here, then it will execute in this memory and write back here. Okay, third instruction will fetch here, and since there is a stall here, it will also stall here. Okay, it will also, in this cycle nothing will happen here. But now suppose there is a again there is a fourth instruction here, so it means that can you fetch it here? This is the question, right? Because we have stalled this, so it means that you cannot fetch a instruction also here. You cannot fetch means if you stall the instruction in this phase, then all the previous module, because at which phase you have stalled, means you have stalled the means data path in execution phase, right? This is the after decode. Concentrate on this. After decode, when you about to start execution, we need to apply a stall. If we are applying a stall, just remember the data path, complete data path of pipeline. So if you are applying a stall in execution stage, then what is the left side of execution stage? Decode and fetch. So it cannot, if you are applying a stall, it cannot perform any new decode, it cannot perform any new fetch. Okay, that's why it should be all stall here. It cannot perform anything in this cycle. Means in the left side there are two modules for fetching and decoding. These two modules should not perform any new task if you are going for a stall. And in the right side, in every cycle, in the next cycle, it cannot perform anything, right? So in this C, it is not performing anything here. I think I'll not explain the hazard section completely because there are some noises coming out, and I think maybe those noises are also recording in my recorded lecture. So but what I am saying, I have already explained you what is called stall. A stall means this side, if you are going for stall, then you cannot fetch any new data. So what you need to do, how you can prevent fetching new data, you can simply stop incrementing the program counter, right? And you can simply stop writing anything in fetch decode stage, fetch decode register. If you do this, then it will stop writing anything new in that anything new, it will stop fetching anything new. And as you can, if you see this example here, the stall is explained in more detail. See, the first instruction was the load instruction, and then after this, here this instruction is actually this instruction. This instruction was actually this AND export instruction here. But after decoding, when it goes to the execution state, is realized that it cannot execute it. It cannot execute it because of the dependency. So it need a stall here. So what it will do, how it will convert to a stall, it will simply convert this instruction to a no operation instruction. This is called NOP. No operation instruction means if you execute this instruction, nothing would change, no register will change, no memory will change. So it will simply convert to a no operation instruction here, and it will perform. And what will do in the next cycle, as I said, in next cycle, still the fetch decode register will store the old value, because no new value will be allowed to write there. So again, in next cycle, when you will fetch, when it will start decoding, it will again start decoding the AND instruction again. So that's how you can implement the what you can say, stall. So for stall, with forwarding, you can only forward the data. And if there is a if you need to handle the condition like load and immediately followed by a R type instruction, then you also need a hazard detection unit in the decode phase. You can say instruction memory in this phase. So in this phase, you can detect the hazard, and the hazard detection logic is also similar. The way I have explained the logic of what you can say, the forwarding, a similar way you can also find out the hazard detection logic. Because if there is a load and then immediately there is a store instruction, there is a R type instruction, then there will be a there will be a hazard. So it means that the what you can say, the RD of IDEX, if it is depend on if it is depend on what you can say, the RS1 of IDEF or RS2 of IDEF, then there is definitely a and if oh, there is one more thing. And if it's a memory read thing, so there will be memory read signal, right? If you remember the control signal, memory read. So memory read means if you want to read something, then that memory read and memory write, there are two signals here. If it is a load instruction, then memory's read signal will be always high. So in this case, first you will need to check if this instruction is a load instruction or not. So you will check if it is a memory read. If memory read is high, then it will check if the RD of IDEX is equal to either RS1 of IFID or RS2 of IFID. If this is the case, then this is a hazard situation, and this cannot be handled by forwarding. So there must be a stall inserted. So how we can insert a stall? For inserting a stall, you will send two signal here, so that to stop writing in program counter, stop incrementing the program counter. If you increment the program counter, then it will not fetch anything new. So the IFID data will be remain same, it will be same. Okay, and you can see here this control, there will be 0 here. Previously there was only control information is all going, there was no mask here, but there is a mask introduced, and we are also supplying 0. And this control hazard in if it wants to insert stall, it will select this 0 line, it will allow this 0 to pass through. This means all the control information will be 0, and if all the control information is 0, then the instruction will be converted to a NOP instruction, no operation instruction, because all the control signal will be 0. And Then how in next cycle, how it is executing the same instruction? If you go to previous diagram here, see they are saying after detecting a hazard, means hazard, they are converting all this instruction to a no operation instruction, means this is a stall. This is how they are implementing stall. And then add this and instruction, it started with and but it becomes NOP. So again I'm next cycle I'm again trying to trying to execute the AND instruction. How it is possible? Because the register, that is left side registers, are not changing. Why not changing? Because I have already stopped fetching new instruction by stopping anything to write in program counter, anything to change in program counter. So in this way, in next cycle again the same instruction will start executing. In this way we are putting one stall in the data path. So this is from so you can say this data path that I'm showing now, this is the complete data path, including pipelining, okay, including forwarding unit, and including a hazard detection unit. So this diagram is complete, but this diagram has not no control signal to handle the control hazards. So in next class we will discuss that how control hazard can be introduced in a pipeline in this data path. Okay.